The paper we're diving into today is on Einstein-Minkowski-Osiak relativity by David Lush.
Okay, that's quite a title, right? I feel like just saying it out loud almost makes me smarter. But yeah, so this paper by David Lush is basically revisiting, well, challenging actually, some of the key ideas we all thought were settled in relativity.
The core question is, honestly, a wild one. What if the textbook version of Einstein's relativity isn't the only game in town? Lush explores an alternative called Osiak relativity that's based on different mathematical assumptions. Specifically, it argues that if you base your descriptions of particle mechanics on fully Lorentz-invariant Minkowski equations, so four-dimensional equations, rather than the usual three-dimensional Planck ones, you actually get different formulas for energy.
And it's not just some subtle difference. It literally changes what the rest energy, kinetic energy, and total energy of a particle are supposed to be. Apparently, in this Osiak version, the rest energy is E0 equals mc squared by 2, instead of the classic E0 equals mc squared.
Yeah, which, if you love your Einstein posters and mugs, kind of hurts, right? I mean, E equals mc squared is like the most famous equation in physics.
I know! But the significant thing here is, Osiak relativity doesn't conserve energy in relativistic collisions the way Einstein's version does. Instead, it preserves something called the temporal component of 4 momentum. So, for all practical purposes, like the energy thresholds that smash particles together, they still come out right, but the underlying principle isn't energy conservation, it's temporal momentum conservation.
That is a lot to wrap your head around. I love that nerdy distinction, though. It's a reminder that the universe doesn't care about what's in our textbooks. But back up. Does this mean all the observed conservation laws are just aspects of momentum conservation in this framework?
Pretty much, yeah. If Osiak relativity accurately describes nature, then what we've been observing and calling energy conservation is actually a reflection of 4 momentum conservation. Which, honestly, makes me a little dizzy, but...
No, same. Because that's like saying all of these collision experiments we've done, all of physics built on those, maybe our explanation's been wrong, even if our calculations lined up. It's very, you've been using the right recipe, but you don't understand why it works.
Exactly. And Lush really stresses that this isn't just theory for theory's sake. Like, he mentions possible consequences for dark energy and dark matter. That if energy isn't strictly conserved, maybe that missing energy we attribute to dark energy or dark matter is just, the universe not keeping the kind of books we expected.
I mean, it would be kind of poetic if dark energy was just the universe bungling its accounting.
Or being way more clever than our equations. Oh, also, this is a fun side note, and then I promise we'll get back on track. Lush goes off about how, under Osiak relativity, the electromagnetic field should be complex valued, not just real, which could maybe connect to why quantum mechanics uses complex numbers everywhere.
Yeah, that's wild. Like, maybe the math weirdness in quantum stuff isn't just quantum is spooky. Maybe it's just our relativity being incomplete.
And to make it even more spicy, Osiak relativity resolves some persistent puzzles, like the spin-orbit coupling anomaly in atomic physics. In this new framework, the energy levels just make sense without introducing things like Thomas precession, which always felt kind of like a fudge to me.
This brings up a meta point, actually. One thing I keep coming back to, reading through this paper, is how scientific theories aren't absolute truths. They're frameworks. And sometimes we find out the framework we've been using is kind of off. But if it still made good predictions, should we care? Or should we push for something more fundamental, whatever that means?
Yeah. Like, does it matter if it's momentum or energy being conserved, as long as a collider produces the right amount of stuff? Maybe it only matters when we want to explain something that doesn't fit, like dark energy.
And honestly, listeners, that's the kind of philosophical rabbit hole academic research leads us down. Lush isn't claiming he's found the truth, but he's showing that there's more to explore. and sometimes that means turning long-cherished ideas on their heads.
If anything, it's a good reminder not to take textbook physics as unchanging gospel. The real universe might still have surprises up its sleeve, just waiting for someone to reconsider what everyone else took for granted.
Absolutely.